Okay, so there's 4 of you here, so I guess we can get started. So I've begun the process, almost finished the process of grading all of the mini exams. I was a little backlogged on those. So I have just a few more to do for the mini exam 4 grades. And then at that point, I'll have everything graded. I'll have those done hopefully tonight. And I'm doing that because Friday is the drop date. So if anyone is considering dropping the course, at least you'll have like a complete picture of your mini exam grades. Remember, I'm gonna need 4 grades from you for the mini exams. And I just sent out the newest one today. And it's due a week from today, but I think it's only 3 or 4 problems. I need to go check, but yeah, I accidentally sent it to my Cal 2 class. They all freaked out. They all started emailing me and texting me like, what the hell is this? So, but anyways, I sent that out to you. Are there any questions over that, grades or anything like that? No? And then remember, I did say that the final is going to be a take-home final, or I'm sorry, no, I was going to give you a bunch of problems, right? And that the final would be a subset of those problems, right? So just to give you some, picture as to what you should expect going down the road here. Okay, let's get back to business. We were talking last time about the Jacobian determinant and how we can do a change of variables, but anytime we do a change of variables, we always have to include this Jacobian determinant in our new integral. And I started to show the part for spherical coordinates, and then I sent out, did I send a video, or I just sent a copy of the worked out stuff, just to show you how you could simplify everything we did in class and get down to the rho squared sine phi. So I'm moving on. We're going to do now our first example of this and showing a problem where we're going to use this idea of changing variables. And I think we'll see as we set this problem up why it would be useful to do this. So the problem is to use the change of variables. So we're given that we're going to change x over to 1/4 u plus v. We're going to change y over to 1/4 v minus 3u. And we're going to use that change of variables to find the double integral over d of 4x plus 8y dA. And the region of integration is this. So I'm going to start by drawing the region of integration. And then we'll start discussing what happens under this transformation. When I say transformation, I mean we are transforming our variables from x and y to u and v. So that is a transformation. Yeah, that's all I'll say about that right now. So let's plot these points. So if I plot the points, -1, 3, I'm just going to say this is -1, then I'll just go up, I'll just say that's 3 up here. So we have this point, we have 1, -3, so 1, down 3, about right here. I'll label these. The next one is 3, -1s, 1, 2, 3, -1, somewhere around here. And then finally 1, 5. So that puts us up here at 5, 1, 5. Okay, so this is our region of integration. Remember, we are doing a double integral. So our region of integration is going to be something in the xy plane. So if you look at this region, going back to when we first started doing double integrals, this is not a rectangle. Okay, it's not, x is not trapped between 2 constants, y between 2 constants. It's not a type 1, and it's not a type 2, and it's not a polar region. Now you could try and break it up to make it like maybe a couple of different regions where each one would be maybe type 1 or type 2. You could do that. But we're going to transform this region under this change of variables and see what it becomes. All right. So to figure out what happens to this region in the XY plane and what it becomes in the new space, which would be U here and V here, what we need to do is take both of these equations and somehow get them in terms of U. So U equals something, and then V equals something. All right. We need to know what U would be if you knew what X and Y were. So another way I could write this is we need to write U as a function of X and Y. And then we need to write V as a function of X and Y. And that way I can tell what happens to all these points under this change of variables. So in order for me to do that, I'm going to have to do some algebra on this stuff up here. So let me write these down. It's going to be, go back up to that. So first, X is equal to 1/4 U plus V. And then Y is equal to 1/4 V minus 3U. Okay, so let's just start doing some algebra here. I'm going to multiply both sides by 4 here. I'll do the same thing on the other one. And then notice that on both of these, I could solve both of them for V. And if I can solve them both for V, then I can set them equal to one another, right? So if I solve this first one for V, it's going to be 4x minus U equals V. And then if I solve this one for V, I get 4y plus 3u equals V. And since these are both now equal to V, I can set them equal to one another. So I have 4x minus u must equal 4y plus 3u. And now I remember my goal was to try and get u in terms of X and Y. So if I solve this for u, let's try and do that. I'll move all the u's to one side. And I'll bring the stuff with y's or anything that doesn't have u in it to the left side. So I just added u on both sides, subtracted 4y. And finally, let's just divide by 4. So now do you see that u is a function of X and Y, right? So I'm going to go back up here. I'm going to put u is X minus Y. Once I know what u is, I can go back up to either, I can pick here, it doesn't matter which one I use. I can use this or this to figure out what v is in terms of X and Y. So I'm going to just go with this first one. V here would have to be 4x minus u, but we just said that u must be X minus Y, so I need that in parentheses so that the negative distributes here. And we should just get 3x plus y. Subtract the x, add the y, and that's it. So this is 3x plus y. Okay, any questions on this? You're going to see, if you're not quite sure why I'm doing this, you'll see in just a moment what's important with this. All right, so what happens to these points under this these transformations? And I'm going to copy this. I'm going to slap this up here so I can use it. Okay, now some of you have taken linear algebra, some of you have not, but I'm just going to state this. We're not going to get into depth about this. If you look at these change of variables that we were given, right? We were told, let's change the variables in this manner. These are called linear transformations. And the reason they're linear is because all, the variables here, u and the v, are both to the first power, okay? And because they're u and v are to the first power in both of these changes of variables, these are linear transformations. What's important about a linear transformation is that if I have, let's say, a line, let's say if I take a look at this line here, that line under the transformation, if it's linear, will stay a line in the new space. So lines go to lines, points go to points. And that's important because if it was a nonlinear transformation, it may not do that. It may take a line to a parabola, or it may take line to some other weird curve. But because it's a linear transformation, I know that lines will go to lines. And so what I can do in this problem, and only because it's a linear transformation, is I can just figure out what happens to the 4 points under the transformation. Those 4 points are going to go to 4 new points in the new space. And then I can just connect them with lines because it's a linear transformation. Right, Terrence? Because you've done the linear algebra, right? So we should be able to trust that lines go to lines. All right, so let's do it. So let's take a look at this first point here. This one right here. Let's take a look at -1, 3. So -1, 3, and remember this is x and this is y, under this transformation becomes some u and some v, right? But here's the formulas I have for u and v. So let's figure out what u would be. So u would be the x, take away the y. So I'd put -1 here and take away the y, which is 3. And then the v would become 3 times the x plus the y. So 3 times the -1 plus the y, which is 3. So we should get -4, 0. That makes sense? So that point, this point right here, under the transformation, oh shit. Under the transformation, that point into the new space gets dropped off right here at -4, 0. And then I'm just going to keep doing this for each of the remaining points. Once I draw my 4 points over here, I'll connect them with lines, and that will be my new region of integration. So let's do the 1, 5. Let's see where the 1, 5 goes. 1, 5, this is x, this is y, gets transformed into a uv. And so that will become, let's see, u is x minus y, so 1 minus 5. And then 3 times the x plus the y. So y'all check my math here. -4, 8 is what I'm getting. -4, 8. So where's that over here? I'm not going to draw dotted lines, dotted lines to all these, but I'm just going to plot it. It's -4, 8. I'm just going to say that's -4, 8 right there. Say this is 8. So there, I've got that point now. So you could say right now that if we were to be looking at that line right there in green, that actually gets transformed to this line down here that connects those 2 points. Okay, we keep going. So now the next one, let's do this one here. So where does that get you? Maybe we can do it without actually having to write all the work. So the u is going to be the x minus the y. So what should that give me? If I take the x and subtract the y? 4. Okay, and then what's the v?
8.
8. 4, 8. Okay, so where's that over here? Well, here's 4, and 8's up here, so it gets taken there. That one I can do because it's right there. That one went there. And then finally, this one, under the transformation, this point goes to 4, and then I believe 0. So that goes here. And now what we have is this new region. Connecting them with lines because they're linear. This is our new region of integration. And what's great about this region of integration is that it's just your standard rectangle, isn't it? I can say that for this region, my u's are trapped between 2 constants, -4 to 4. and my V's are trapped, sorry, between what, 0 and 8, right? Any questions? All right, now I need, oh, the integral's right there. Okay, so here's what we're trying to do. We're trying to do this integral, okay? So to do that integral, the double integral over d of 4x plus 8y with respect to area will become a new double integral over, let's call this d tilde, okay? This new region, I'm gonna call it d tilde. It's not d, it's d under the transformation, all right? So it's a new double integral, and then what it'll be, I'm sorry, it's a new region. And then what it'll be is 4 times x, but we can't put x there, right? Because we've switched everything over to u and v. So it's actually 4 times, well, what's x? Well, that was given to us, right? What we're going to change x into? X is 1/4 u plus v. So this is 1/4 times u plus v. And then plus 8 times y, but y was given to us up here to be 1/4 times v minus 3u. So this is going to be 1/4 times v minus 3u. So the thing that we're doing right now, if you haven't kind of caught on to this, what we're doing right now is equivalent to when we're doing polar and we have to replace x with r theta and y with, x with r cosine theta, and we replace y with r sine theta. This is that step where we're replacing the x and the y with something in terms of our new variables. But see, r cosine theta and r sine theta are nonlinear transformations. So that's why you can't just draw points and draw lines when you're doing polar conversions. It's a little more complicated. Okay, so we've got the new double integral over d tilde. Here's the function, but now converted from x and y's to u's and v's. What do I still need here next to this?
That conversion factor we were looking at.
Yeah, it's like a conversion factor. It's that Jacobian, right? It's the absolute value of that Jacobian. I'm just going to use capital J for Jacobian so I don't have to write it all down. And then this will be with respect to area. But this time the area we're talking about is an infinitesimal patch here in the UV plane, not in the XY plane. So we still need the Jacobian, right? We still need the Jacobian. So going back to last class, or yeah, no, I had it on that page. It was ready to roll. Sorry. The Jacobian is right here. Well, the Jacobian is this part, and then we just take the absolute value of it. So we need to do this, right? And I'm sorry, I'm kind of running out of room. Let me just do it on the next page. So we want to do this, and we are working with, clear all this crap out of here. Here is our change of variables that we made, right? So we're going to look at these and take the partial of x with respect to u, multiply times partial of y with respect to v, subtract partial of x with respect to v times partial of y with respect to u. Okay, so I'm going to try and do all of this right now, okay, without, well, maybe it'll help if you just distribute the 1/4 through. It'll be easier to do the derivatives here. I mean, it probably isn't, but just in case. So this is what x is. This is what y is. So the partial of x with respect to u would just be 1/4, right? Just the constant in front of u right here. So this is 1/4 times, now the partial of y with respect to v, which is again 1/4. That's just the constant in front of the v there. And then minus the partial of x with respect to v, that's going to give us the constant right there, 1/4. And then the partial of y with respect to u, so it's just the constant in front of the u there, which is negative 3/4. So this gives me 1/16 plus 3/16, which gives us 4/16, which is 1/4. Now, the Jacobian here turns out to be a number, doesn't it? So I'm not sure who said it's like a scalar factor. Did someone say that? Scalar factor? Did someone say that?
I said conversion factor.
Conversion factor. Okay, yeah, okay. So it's a conversion factor. In this case, yeah. So I thought he said scalar. This is a conversion factor, but it turns out to be a scalar, right? Like all we're doing is by making this transformation, our original region, we're having to compensate for the transformation by scaling it by 1/4 in order for everything to work out. When you do a polar conversion, it's not a scalar, right? It's actually r, which is not a number, it's a variable, right? And when we do spherical coordinates, it's rho squared sine phi, which is definitely not a scalar, but it still is a conversion factor, it's just not a scalar. In this case, it is, all right? So now I'm gonna go back to this. Here's where I was. And I'm gonna actually, let's go ahead and use the fact that we have our limits of integration here and they're constants. So this will be, they're between constants. So I can just, the order of integration doesn't matter here. I'm gonna go -4 to 4, 0 to 8. And then I'm gonna have here, let me just go ahead and those 4s go away. I just get u plus v. And then over here, distribute, I get a 2 there. So I get plus 2v minus 6u. And then I have to hit all that with a 1/4. I don't need the absolute value of it because it's already a positive number. dv du, because the u is the outside one, right? -4 to 4, 0 to 8. -5u plus 3v. 1/4 I'll pull to the outside of the integral because it's a constant, dv du. And then at that point, it's pretty straightforward. You just integrate with respect to v, which will be pretty easy because these are just, just be powers of v or powers of u. Plug in 0 and 8, and then go and integrate with respect to u. Okay. I'm going to stop there. Are there any questions? Was that worth all that effort? I mean, that took us 20 minutes. Could we have maybe done the original problem by now if we would have broken it into like, type 1 region, type, you know what I'm saying? Like, was this even worth it to do all this? You know what I'm saying? I don't know. I think you could argue. You could argue that maybe you could have done it the other way and you'd have been done by now.
Probably not on a simple problem like this, but on a more complex one.
Yeah, but there's actually a more profound question here. And that is, does anyone realize like what there's an issue with this example. Like there's something that we've taken for granted here that should bother you a little bit.
It's just a rectangle, length times width. And we could have been done.
What do you mean? Not sure I follow you.
Well, I don't know. I could have just taken this rectangle I have on a 2D plane and went back to grade school and did length times width and would have been done in 30 seconds instead of 20 minutes. Just for
But we're
this,
not-
just for this. I don't know if that's the profound question you're looking for, but
Well, it's not, but I want to be clear. We're not finding the area of this. That's not what this integral represents. This double integral represents the volume of the surface that is above this region in the XY plane. So remember, this is a function of 2 variables. So in reality, we have our original problem with some weird region. I'm not going to draw it like this was our weird kind of region on the ground, right? and we have some surface above it. And if you project that rectangle up into the here, we're trying to find that volume underneath it.
My bad. For a second, I forgot we were doing volume. I just saw
Yeah.
the square and thought. There.
Yeah. Yeah, if the original problem would have been the double integral of 1 dA, not 4x plus 8y, but if it was just 1, then yes, we could have just found the area. But there's something else. I mean, if let's say you were trying, I just threw this integral at you right here. I said, there you go. Well, here. I said, there you go. Do this integral over that parallelogram. Okay. There's the problem. Well, how in the world are you going to know to do that transformation? Right? Like where's that transformation? Where's the motivation behind that transformation? I gave it to you, and now you're seeing that it actually makes the problem work out. But like, how in the world would you come up with that on your own, right? Like, where would that come from? It's not just given to you, right? And that's a very valid question. And this example is just to show you that if you do a transformation, don't ask where it came from. If you do a transformation, that you can make certain regions look better and the integration becomes easier. Understand? Or the problem becomes easier. So the next example that I'm going to give you is exactly what the issue that I just said, you know, we were given the transformation here, we are not. But it says, use a change of variables to find the double integral over d of e raised to the x plus y over x minus y dA, where d is this trapezoid. Okay. So it's not telling us what to use. So I'm going to just start by drawing, I'm going to draw the d. Okay, I'm going to draw the region of integration in the xy plane first. All right, so let's see. 1, 0, I'm going to say that that's 1, 0. And then 2, 0. And then 0, -2. And 0, -1. So there's D. Now, one could argue right now that you could just split this up. Okay, like right now, if I split it right here, I could do like this region right here would be a type 1 because x is between two constants and the y is between two functions of x. And then I could do this one, which again is x is between 1 and 2 and the y's are between two functions of x. So I think splitting it, do you all see that we could do like 2 type 1s? So you might be sitting there, well, that's what I'm going to do because I don't want to go through all this transformation shit and I don't even know what the transformation is, right? But I challenge you to try it because if you try it, you're going to get stuck. You're going to go and you're going to try and integrate this. And let's just say we do this with respect to y first, okay? Who cares about the limits of integration right now? Just if you had to integrate this with respect to y. Good luck, you know? It's not happening for you. There's nothing that you're going to be able to pull out of Cal 2 that's going to allow you to do this. And I showed you all this at the end of class last time, I think, didn't I? Didn't I go to let me see, where's my Wolfram? I'll bring it up so everyone can see it. So I'm just going to do integrate e raised to the x plus y over x minus y with respect to y. See what it does. Oh, actually, that didn't do too bad. Oh, I typed it in wrong. Oops, do y'all see that? I typed it in wrong. how is that? Maybe not.
You didn't hit the power sign.
Oh, I did not hit the power sign. Thank you.
Yeah.
Okay.
Most other programs don't even attempt to do this integral.
Yeah. Like Symbolab,
Yeah, it just straight up tells you don't even try it.
it says, go drop the class, right? So look, I mean, this, okay, gave us an answer, right? But it's 2x EI. What the hell is EI? Well, EI is the exponential integral. Okay, so we've never studied this. And if we look into it, the exponential integral involves complex numbers, imaginary numbers, and it's a field that we have never even studied, right? Okay, so it's not happening. And so we're kind of stuck at this point, okay? We're stuck unless we know complex analysis, which we don't. So maybe this is why the change of variables is good. Okay, maybe it's good. And the thing that you need to look at, because remember, we still have to figure out what's the change of variables we're going to make, right? What is it that we're going to do? The thing that makes this thing a problem is the fact that when we integrate with respect to y, it's not that we have a y up here, it's that we also have a y on the bottom. It's that division. Do you all agree, like if this whole thing wasn't even there, we could integrate that with respect to y pretty easily? I hope that you see that we could. It's the fact that we've got a quotient that has one, but the variable in both places. And that goes for the x and the y. So that's the problem. But that also might be like recognizing that that's the problem might also be the key to figuring out what substitution, what transformation we should make. Anybody have a guess? If the problem is that the variables in the XY space, the X and Y appear both in the top and the bottom, how can we do a transformation where the two new variables will not appear together in the numerator and denominator?
Make the numerator U, the denominator Y, V.
Yeah, let's try it. What if we make, okay, so here's transformation. What if I'm going to say U is going to be the X plus Y and the V is going to be the X minus Y? Just think, before we actually go about this, just think about what this new double integral would look like. E to the U over V, and then D whatever, who cares, okay? But if I asked you to integrate that with respect to U, you should be able to do it because you're going to treat V like a constant. If I ask you to integrate that with respect to V, it's okay because you're going to treat U like a constant. You can't do that over here, right? Because it's in both places. So this looks like promising, right? That we're happy about that idea. Now we're not sure if it's going to work. And another thing that Terrence would tell us, because I know Terrence is taking linear algebra. That's the only one of you that I know is actually taking linear algebra. Terrence will tell us that this transformation is linear also, right? So that'll be nice because all we'd have to do is figure out where those 4 points go. And wherever they go, I'm just going to connect those points together with lines, and that'll be my new region. So it seems like a really good choice for U and V. Do y'all agree? All right, let's continue then. All right, it should be easy for us to figure out where these points go. So in black, I'm going to label these points. This was 1, 0. This was 2, 0. This was 0, -1. This was 0, -2. All right, I'll do it in a different color. I'll do it in blue. Let's talk about where each of these points go. And I don't even have to solve for U and V, do I? Like we defined it, like, we said, let this be, right? We established that, right? So now if I just want to know what U is, let's see. This turned into a UV. The U would be what? So U is X plus Y, right? So the U
Would be 1.
1, and the Y would be, I'm sorry, not the Y. The V would be X minus Y. So
1.
1 again. Okay. This one will become what?
2, 2.
2, 2, right? This one would be, let's see, u is going to be the x plus the y. So just -1, right? And then the v would be the x minus the y, but minus and negative would become plus. So -1, 1. And what about this last one here?
-2.
-2, 2.
-2, 2. Okay. Let's go ahead and draw that in the UV plane. So in the UV plane, I have the point 1, 1. I'm just going to put it here, 1, 1. I have the point 2, 2. I have the point -1, 1. And -2, 2. Connect those with lines. Who's going to make me happy and tell me what type of region that is?
Yes.
Type 2.
A type 2. This is a type 2 region because now we can't say our y's because we're in the UV plane. Our v's are stuck between two constants. What constants are the v's stuck between?
1, 2.
1 and 2. Okay. Now the hard part. What are the u's stuck between? So take a look at this black part right here. I'm going to zoom in on this a little bit so we can see what's going on. Okay, so this right here, if we were to extend it down, this is like y equals x, isn't it? Isn't that like y equals x? But because we're using v and u, this is actually v equals u. And if v is stuck between two constants, u must be stuck between two functions of v. So if I solve this for u, I just get v up here. And if we look at the bottom piece here and extend it, this would be like y equals -x, or for us, v equals -u. Y equals -x, same as v equals -u. And if I solve this for u, I get u is -v. So that's my lower limit. Is this all making sense?
Yeah, this makes sense.
Okay, so I would say that the region is not that great, okay? The region we got isn't that great. What's great is the integration is gonna be easier, all right? That's the part that's gonna be good. Now, I think I'm almost ready. We're missing our Jacobian. We don't have that yet, do we? We need our Jacobian determinant?
Sir, could we also just, I mean, solve it by symmetry?
How do you mean?
Well, on the v-axis, it splits it down the middle. Could we just multiply by 2? Solve for one.
Great question. I guess what you're asking me is, could we have just done, instead of this, go 1 to 2, but then go 0 to v, and then just double our answer? What do y'all think?
I think that would work.
Depends on the region above it.
Depends on the region above it. It depends on the surface above it. Remember, this is only the domain, right? So we have a surface floating above it, and we're trying to find the volume down to this region on the ground. If the region above it is symmetric over the axis like the region is, then yes. But if it's not symmetric, then no. And I don't think it's going to be symmetric because it's an exponential function. And exponential functions generally are not symmetric over like the y-axis, so to speak. That makes sense?
Yeah.
Great question. Great question. Anytime we can do that, we want to, right? Let's just make our lives nicer. But we have to understand within the geometry of the problem, we would have to have both the symmetry here and the symmetry above. Okay, Jacobian. Uh-oh, we have a problem. Jacobian. What's wrong when we start to go figure out the Jacobian? We need the partial of x with respect to u, right? We need the partial of x with respect to u.
We need to
So
solve for X and Y.
we need to try and get these both in terms of x equals some function of u and v, and y equals some function of u and v. So in the previous problem we did, remember the transformation I gave you were in terms of x and y, like x is equal to this, y is equal to this, and then we had to go solve them for u and v so that we could figure out where the points went. In this problem, we came up with the transformation in a different light. We figured out what u and v were in terms of x and y, but to do the partials, we've got to get it back the other way. So I'm just going to do the same thing we did before. I'm going to, let's solve the first one for x. So if I solve that first one for x, I get u minus y equals x. If I solve the second one for x, I get v plus y equals x. So I'm just taking both of those, solving them both for x, set them equal to one another. Move all the y's to the right, u's and v's to the left. Divide by 2 or multiply by 1/2. Y'all get what I did there? Solve for x, set them equal, solve for y, there we go. Now that we know what y is, I'm just going to take that one and replace the y with 1/2 of u minus v, and then equals x. This becomes v plus 1/2 of u minus 1/2 of v equals x. This means 1/2 of u plus 1/2 of v equals x. So 1/2 u plus v equals x. Questions? Now we can do this. Partial of u with respect, partial of x with respect to u. So I'm looking at this one. With respect to u, I'm just going to get the 1/2 in front here, right? If I distribute that through. Do I need to distribute, or can I just put 1/2? Y'all happy with that? I'm getting some looks of not sure, so I'll just distribute the 1/2 through on both of these. So if I take the partial of x, that's this, with respect to u, that goes away, and I just get the constant in front of here. Times the partial of y with respect to v, so now I'm looking at this one, and this one's gone. This one right here, I just get the constant in front there, negative 1/2. And minus partial of x with respect to v, that's 1/2 again, and times partial y with respect to u, which gives me another 1/2. Negative 1/4 minus a 1/4 again, which gives me negative, I'm subtracting, so negative 2/4, which is negative 1/2.
I have a question.
Yes.
Will all linear transformations give, what's it called? Make the Jacobian just go to some constant?
I think that you can answer that yourself. Think about it.
I mean, I feel like it would, because in all
Each of these
cases,
partials is just going to be a number. Why? Because in your expressions, you only have u or v to the first power, right?
Mhm.
So you know that when you take derivative of it, it's going to vanish and you're just going to get the coefficient in front, right?
yeah,
So yes, that is correct. If you have a linear transformation, then your Jacobian will always yield a constant, some sort of scalar.
all right, works for me.
Good.
Just wanted to make sure.
No, that's good. That's a good insight. All right, so I think we're ready, right? I think we're ready to put the integral together. We are going to try and rewrite this integral right here. Isn't this fun? Okay, this becomes the new double integral over d tilde. I didn't really label it d tilde, but I'll just, oh yeah, I did, never mind. And then it'll be e to the, I'm now replacing, right? So we said that x plus y was u. And we said x minus y was v. And then I have the Jacobian, right? I have to multiply by the Jacobian, but it's always the magnitude of the Jacobian or the absolute value. So there's going to be a half here. If you want, you can put negative half and put in absolute value if it makes you feel better. And then dA. Now, I do not have a choice on the order of operation or order of integration now. I don't have a choice because this was a type 2. So I've got to go, this is equal to, let me bring that 1/2 out. Integral. Now my v was between 1 and 2, and that forces my outer integral to be with respect to v. Then my inner integral is going to be my restrictions on u, which is negative v to v. Then I have e to the u over v du. Equals dot dot dot. And that is integrable. You'll be able to take the antiderivative of that with respect to u. Do I need to or no? I'll show it real quick. If I had to take the, I'll do it right here. If I had to take the integral of e to the u over v with respect to u, I would look at it this way: 1 over v times u du. So if I was trying to do this inner integral right here, I would look at the v as a constant and bring it out front as 1 over v. And so the antiderivative of that should be itself, but you have to scale it by what?
Derivative of the power.
1 over the derivative of the power. So you would have to put a, v out here. Think about this. If I take derivative of this and v is a constant, the derivative of this would be itself, boom, 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 that right there. Okay. Then times derivative of what's up here with respect to u, which would be 1 over v, but then that gets killed off by this v. So that should give you this. I'll let you do that. That's stuff that you should be able to handle. I'm done with this problem, okay? Questions, comments, concerns, complaints? I just emailed out a mini exam. I just want to, normally I don't go through these, but I'm just going to show you this mini exam that's due in a week. The reason I made it a week from now is because there's only 3 problems, all right? So the first problem, we have not done this, but all I do is I define something. I say the average value of a function over a solid is given by this formula right here. Okay, so I give you a formula where v of e is the volume of E. Using this information, find the average value of this function on the region enclosed by this paraboloid and z equals 0. So you're going to use this definition I give you to figure out the answer here. I think you can figure that out. It's just a triple integral. I hope you can. The second one, use spherical coordinates. So I'm telling you in this problem, use spherical coordinates to find a volume. Okay. Spherical coordinates means you're doing a triple integral, right? And if I'm asking you for the volume, then you're doing a triple integral of 1. But you got to get your limits of integration set right there. And then this last one, use a change of variables to evaluate this. Looks like the problem we just did, but it's not quite. And then here's the corners here of some region. It's a rectangle with those corners. All right. So after what I just showed you, you should be able to do this right now. And then I also don't tell you what to use, right? But I think after the problem we just did, you could probably guess as to what would be worth going after there, right? Okay. You all ready? Move on. So we are officially done with chapter 12. So we are moving into chapter 13, the last chapter of the textbook. And it's called Vector Calculus. And so the very first section of this chapter is called vector fields. I realize some of you have looked at vector fields before in other courses, physics maybe, engineering. So we're going to just look briefly about, at what a vector field is visually, and then we will start working with vector fields. So a vector field in two-dimensional space. Let me make this a little bit bigger for us. A vector field in two-dimensional space is what we're going to define here. It says let D be some set in the plane. So you've got some, you've got the whole plane, and you look at some set within that plane. So some region within that plane. A vector field on D is a vector function, capital F with a vector over it, or that little, it's like a half arrow, right, on top of it, that assigns to each point XY in the domain D or in that region D, a two-dimensional vector, which we call f of x, f capital F vector f of XY. So a good example of a vector field is a magnetic field. So if you put like two magnets next to one another and you have these little iron little filings and you scatter them around, they'll take the shape of the magnetic field. And so the way that look at this as a vector field is that if you go to any point, just pick a point, okay? That point has some X and Y coordinate, right? The X and Y coordinate is just the position of that point. The vector field is a vector that is being assigned to that point that points in some direction and has some length. So maybe the vector that's assigned to that point would look like, I don't know, like this. If we pick another point somewhere else, like here, maybe there's a vector pointing somewhere and has some length there. So maybe it's like this. And maybe the longer the vector is, signifies more strength to the field. So short vectors, you have a small magnetic field. Long vector means you have strong magnetic field. So the closer you get to the magnet, the stronger the field is. Does that make sense? Or the stronger the magnetic field is. So the thing is, when you look at this visually, right, you're just looking down at this flat sheet. For every single point in here, there is a vector. So if we were to graph all the vectors, it would just be this huge mess of vectors, right? But they're there. At every point, there's a vector, but we can only like visually look at a few of them at a time, or else it just becomes just a cluster of mess, right? Understand? Another two-dimensional one would be if you think of like a hill, right? You think of a hill and you look at it from the top, which is called a topographical map. Then if you were to like set a ball down at any single point, for each point you set the ball down, you could draw a vector that would show the direction the ball would roll, and then the length of the vector would basically tell you how steep it is at that point. So small vector, it's not going to roll very fast in that direction. Long vector, it's going to roll real fast. So the length of the vector would represent steepness. That makes sense? Now we've actually studied this already a little bit. When we were talking about the gradient vector, we studied this. So this we've kind of seen a little bit of. Okay, that's what two-dimensional vector fields are. So here's a couple of examples, okay? So sketch the vector field, capital F of XY equals negative Y, X. So the way this works is you just pick a point, okay? So let's just pick a point. let's pick the point 0, 0. Let's see what's happening at the origin. If I take this through the vector field, it spits out a vector, and that vector is going to be 0, 0. So you can see it right here. At 0, 0, the vector is 0, 0. The 0 vector is basically not a vector, right? It's kind of a special vector. So let's go to another point. Let's go to the point, how about 1, 0? That would be about right here. If I move there, what does the vector look like? The vector field look like there? So I plug in, let's see, the vector field says you take the negative of the y coordinate, which in this case would be negative 0, and then x coordinate, which would be 1, which is the same as the vector 0, 1. But isn't that just a vector that points straight up? So let me move out there and let me show you that vector. There it is. I'm at the point 1, 0, and the vector that's coming out is the vector 0, 1. I could do this for any point I want. Let's go to a more interesting point. How about the point 1, 1? If I do that, what vector gets spit out here?
Negative 1, 1.
Negative 1, 1. And that means it's going to point to the left and up, right? Like to left 1 and up 1. So let me move to that so you can see it. If I move to the point 1, 1, right there, do you see that this is the vector negative 1, 1? Right, to the left 1, up 1. From this point to the left 1, up 1. And I can start doing that everywhere. It doesn't matter where I move. So just go move around the space and you'll see that for every point, we have some vector. So let me have the computer graph a few of these for you. First thing I want to point out, these vectors that are drawn by the computer are not drawn to scale. Okay, so they don't match up with what's happening in reality. Okay, what's happening in black is the actual vector. The computer is just showing me the tendency of the vector field. And it says that as you move away from the origin, the vectors get longer. And they also seem to want to like wrap around. And as you move, they start to kind of twist around. And I can have it do more too if you want to see a lot more of them. Here's a lot more. So you get this almost like this twisting effect, right? It's almost like this twisting effect. If you think of this as like wind or something, then if you're at the origin, nothing would be happening. And if you moved out a little bit, you'd start to feel this circular wind, right? This thing that would want to kind of start moving you around in a circle. And the further away you get, the stronger that is. So the faster you'd start spinning. Does that make sense? If you were like a little leaf being blown around in the wind. That's just one example of a two-dimensional vector field. We could go on, just doing more and more. So let's look at, this is a general one. So I am going to let you tell me what you want the vector field to be here. So I want you to define it however you want. Just give me a definition of a vector field. It's gonna take an input of X and Y. Okay, so it takes the point, and then what do you want it to do with that? However you want.
Can it be easy? Can it just be X and Y?
Itself?
Yeah,
Yeah.
I'm tired of hard math.
Okay, so let me do that. If this was X and the other one was Y, then let me move around. Here's what it would look like. Boom. Basically, that vector field just wants everything going away from the origin, right? And the further away you go, the faster you go. What would happen if we change it? I mean, I'm not trying to make your life harder, Daniel, but what if we did X squared Y?
I'm sure we get some type of curvature.
Yeah, so now this looks a little different, doesn't it? It's hard to see this. So it's not as uniform as the previous field, is it? It's not as uniform. How about if we do x squared plus y? Changes it a little bit. What if instead of instead of y, what if I do sine of y? Nothing says we can't have a trig function. Let's take the x squared off. Just make it x. Okay, so a vector field can be anything. All right, it doesn't have to be nice little like x, y, or negative x plus, y. It can be trig functions, exponential functions. Doesn't matter. Okay, as long as for each point on the plane or in the domain, there is a vector assigned to each point. That's what makes a vector field. Now, what about three-dimensional vector fields? So this is a visualization of the magnetic field of the Earth. So now in a three-dimensional setting, for every point in three-dimensional space, you have a vector assigned to each point. So if I pick some point here, there's some vector pointing in some direction. Pick another point, I've got another vector. Pick another point, I've got another vector. And they're everywhere. Okay, so the vector field is nowhere but everywhere at the same time. It's very difficult to graph a vector field in three-dimensional space. Here's a specific example of one. I'm not going to start picking points. I'm just going to show you what it looks like. But let me move the vector around here just so you can see. I'm changing the x, y, and z of this vector and seeing that, for every position, the vector is changing. And if we were to put all the vectors together and get some idea of what it looks like, there it is. There's the vector field for this particular field. Let's see. Yeah, that's too many of them, I think. Hard to see what's going on there. Oh, that may not be enough. But I think this one gave us the best idea kind of like what's going on. Here's a really important vector field. So I want you to think about this vector field before we graph it. The square root of x squared plus y squared plus z squared, that right there. Okay, if I were to give you this vector, negative x, negative y, negative z, then if I ask you to find the magnitude of this vector, you would take the square root of the sum of each of those, right? The sum of the squares would be x squared plus y squared plus z squared. So now if you divide each one of those by the length, then what can you tell me about every vector in this vector field? How long is every vector?
1 unit.
1 unit, okay? Now, the fact that you have a negative on the x, negative on the y, and the negative on the z, watch what that does. I'm going to just start moving a vector around here. Okay, it's hard to see this, but
They're all pointing at the origin.
yeah, it's like a vector that points at the origin. No matter where I move, I'm going to start moving this thing around it. It's like this creepy person that just wants to keep looking at the center, no matter where it is, right? Which is always looking at the origin. So if you look at all the vectors, or if you get a feel for the vector field, they're all pointing in. And do you notice that they're all the same like thickness? The computer's showing them as all being the same thickness. That's because they all have the same length. Whereas the previous example, these had different thicknesses, which represented a different length for each vector. So this vector field is a great representation of gravity, because if you're on a sphere, right? And so in three-dimensional space, you're on this sphere and you're living on the surface, then at every point on that surface, you have a force going into the center of the sphere. And it's, I mean, for most computations, it's uniform. I mean, the Earth isn't even a perfect sphere. So we know that there's variations in gravitation depending on your altitude and things like that. But just as a general starting point, this vector field is perfect for representing gravity. Do y'all see that?
I have a weird question.
Okay.
So does that mean for any one of those vectors, it would be like a negative normal vector to a tangent plane?
For a sphere, yeah.
Okay, I was
Yep.
just curious.
If you had a sphere centered at the origin, then if you drew, so if I just pick any point on this sphere on the edge and draw a tangent plane like that, then one of these vectors would in fact qualify as a normal vector for that plane, because it would be a center seeking, here's the origin, it would be a center seeking vector like that. Yeah, so if you knew the point, you already know the vector, right? The vector is -1, -1, -1 would work. So anyway, okay, clear. Now, vector fields are very general. A vector field can be any vector function that you can come up with out of your brain, anything you want to put in there for the, it's like you have complete freedom to throw whatever you want here and here, or in three-dimensional, you have X, Y, Z, you'll have a vector that has 3 components. You get to pick. That's generally speaking, a vector field can be anything you can come up with, all right? Anything you want. But there are specific vector fields that are very important to us, and these are called gradient vector fields. And gradient vector fields aren't just these things that you randomly just generate out of your brain. Gradient vector fields are the vector fields that are created when you find the gradient of some scalar function. So little f of x, y, remember, should be a surface, shouldn't it? That should be a surface in three-dimensional space. We defined back a few sections ago what the gradient of f was, and we said that all it is a two-dimensional vector. It's partial of f with respect to x, partial of f with respect to y. Do I remember doing that? We use this to find directional derivative, things like that. So at the end of the day, this is a two-dimensional vector, isn't it? And if it's a two-dimensional vector, then it qualifies as a vector field, and we could call it capital F and say that that's a vector field. And we do, and we call it the gradient vector field, okay? And in three-dimensional space, same thing. So if you start with the scalar function and take its gradient, you create a vector field, and that is called the gradient vector field. So here is an example of a surface. I included the picture of it. And what I'd like for us to do is find the gradient vector field. So the gradient vector field means that we want to find the gradient of f, which should be the partial of f with respect to x, and then the partial of f with respect to y. And that would be, what's partial of f with respect to x?
That'd be 2xy.
2xy, and then the partial of f with respect to y?
That'd be 1 minus 3y squared.
X squared minus 3y
Oh,
squared.
I'm sorry, x squared.
No, that's good. You're good. Don't apologize. At least you're responding. That's good. All right. Y'all with me? Now, I'm saying that's a vector field. It's a two-dimensional vector field. So I'd like to show it to you. So imagine that we are going to look at this surface from the top and look at its domain on the ground. Okay. So here's the domain on the ground. Don't just ignore all these lines for a second. Here comes the vector field. Yeah, let's do that. Make it a little bit bigger for us. Okay. There's our vector field. So I need to turn this so it matches. There we go. This is the vector. Come on. Come on. It's not letting me turn it the way I want. I think you get the idea. We're looking at the surface from the top, okay? Let's take a look at what these vectors represent, all right? Let me make sure I have my X and Y proper here. So look at these vectors right here. Notice that they are pointing towards the origin and they're getting smaller, right? They're getting smaller. If I take this surface and I turn it this way, I need to curve it. It's kind of like, I need to draw it with my marker on here. It's kind of like, let's say we take this point right here. That would have a vector that looks like it's pointed that direction like that, right? On this surface, it's there and it's pointed that direction. It's pointing in the direction of steepest ascent at that point. If I go back to a point that's further back, like back in this corner over here, it's going to point like this. That's like a point that's way down here on that curvature of the surface down. And so the vector is pointing this way in the direction of steepest ascent. If you take a point like along this edge right here, hold on, I'm getting an error here. If you take a point like this one right here, it has a little vector going that direction. And that would be like a point right here, wanting to kind of go up a little bit, up that little ridge right there. Do y'all see how this corresponds? The vector field represents the gradient vector field, shows us at each point, the direction we should go for steepest ascent. And if you go the opposite direction, right, if you just multiply that vector times -1, you'll be going in the direction of steepest descent instead of ascent. So I've always found this is amazing because the computation, if someone gives you a surface, the computation to figure out like what direction you need to go to get, steepest descent is not a hard computation. It's very simple. It's just a gradient vector field. That's all it is. Do I have any questions?
Seems strangely simple compared to the previous chapters.
Yeah. Okay, we move on. So I know some of you who've taken physics have heard of this before. What is a conservative vector field? All right. So we're going to define it here. A vector field F. Now, remember, I just told you just now that a vector field can be anything that you come up with, okay? Anything in your mind. A vector field F is called a conservative vector field if there is some scalar function F such that that vector field is the gradient of that scalar function F. Okay, what is that saying? Okay, what it's saying is, how we just did this problem? We came up with the gradient. This was 2xy x squared minus 3y squared. And we just said, hey, at the end of the day, this is just a vector field, right? If I ask you right now, is this vector field conservative? You would say yes. And the reason it's conservative is because it came from taking the gradient of a scalar function. not all vector fields can be generated by taking the gradient of a scalar function. Not all of them can. Any vector field that can be generated by taking the gradient of a scalar function is called conservative. Otherwise, it's not conservative. So, yeah, we are going to revisit that. Trust me, we're going to do a lot more with this. This is just to give you a first kind of like introduction to the idea of conservative vector fields. It just has to be the gradient of some scalar function. All right, that's it for that. This is just an introduction to vector fields. Now, we are not going to go immediately continuing to work with vector fields right now. Okay, this was just an introduction. We're going to step away from vector fields for just a little while and go back and do something else right now. It's the next section, but it seems like naturally you'd want to continue talking about vector fields right now, but I just want you to put it on the back burner. We are now going to talk about 13.2, which are called line integrals, also referred to as curve integrals. All right, here's where things start getting pretty messy, all right? I was looking through my notes. I was looking through my documentation that I have for this class. And when I get to my notes for everything I have a special set of notes here just for the chapter 13, section 2. Just the formulas from this section. And if I open that and I'll show it to you, these are the formulas just from this section alone. Page 1, page 2, page 3, page 4, page 5. That's this section alone. There's this much in here. And so in the beginning of these formulas, you'll notice there's no, do you see any vector notation at all? Do you see any like half arrows on top? No, right? Page 2, no vector notation yet. Page 3, no vector notation. Page 4, no vector notation. Finally, page 5. Now we start bringing in vectors. So in this section, we will talk about vectors, but it's not till towards the end. We kind of bring it all together. All right.
There were vectors on page 3.
Were there?
Yeah,
Where?
towards the end of it. Right there.
Oh, yeah, right here. This is, yeah, I take that back. There's a way that you can convert that, but these aren't vector fields. Okay, this is a vector function. We've studied these. This is a vector function that draws a curve. Okay, that's what this is, as opposed to this, which is truly a vector field. That capital F is a vector field. So look, what we're going to try and lead to here, and just to give you kind of like some preview as to what we want to be able to do in this section. And this is just to kind of make you feel like you can keep your sanity because of all the things you're about to see. Imagine you have a particle that you want to move through space, okay? And you've got some sort of gravitational field acting on this particle. Well, you have sometimes when you're moving through that space, the gravity is helping you, and sometimes it's actually making you having to work harder, right? We want a way of calculating the amount of work required to move some particle through space. As you move this particle through space, you have a vector field the entire time. There's a vector field, right? And so at every point on that path, you have some computation of a force in some direction. And we know that, well, do we know what the definition of work is? We will talk about it more. If you know what it is, great. If you don't, no.
So force over a distance.
Yeah, it's the computation of work is a force applied over some directed distance. And so if you're moving a particle along, then you have force. At every point you have a force from the gravitational field, and then you have some displacement that you're moving. And so we want to add those all up as you move through the path. And to add them all up requires an integral. So that's kind of what we're trying to do, is, at least in this section, we're going to get to that point. But to get there, we first have to start with the basics. So we have to be able to do these things called line integrals. Go ahead.
Is that how you, I was just wondering, is that how you compute gravitational waves?
How do you mean?
You said it's a particle moving throughout space, and like at it has a vector at each point.
Mhm.
I was just wondering, like, is this what you're teaching right now? Is that how you compute gravitational waves?
I'm not quite sure what you mean by gravitational waves, how you compute them.
Like, how is that how you solve the point that they're at?
No, I don't think we're talking about the same thing, because when we're moving a particle through space, our vector field is the actual gravitational field, which would be some vector field. So we would be given the vector field and then calculating the work done to move the object through the space. I think what you're asking me is this a way to calculate?
Yeah, I guess
something?
more so the wave rather than the, yeah, I don't think I asked that correctly. I was thinking more of the wave, but that's not this. Yeah, okay, thank you.
That's probably beyond what we're going to do at all ever in this class, is what you're asking.
Okay.
Okay, well, let's take a step back. We don't have a ton of time left. This, I think, this first part of this section, I think you'll be somewhat pleased to see, because it's very geometric and I think easy to follow. So the first part here says, suppose we have a function f of x, y, which is a surface, and we have this surface kind of just hanging out here, right? Just the surface. And then what we do is we restrict, we draw a curve C in two-dimensional space on the ground. So the red part, that's my C, okay? Some curve in two-dimensional space. And what I do is I take each point in that curve and I map it up to the surface. Each point goes up here. Then when I do that, I'm going to draw a curve up on the surface, right? If just those red points are allowed to go into the surface, then I draw that blue curve, right? The question is, what would the area of the curtain be if I dropped it down from that curve? I'm not talking about the volume underneath, like what we've done in the past is we've done some region on the ground, some surface on top, and we've looked at a volume of something, right? The volume below down to the ground. This is different. We're saying instead of drawing a region on the ground, draw a curve on the ground, map those points up into the surface, and it draws like a curtain, and we want to know the area of it. Understand that that's a fundamentally a different problem than finding a volume. Now, it might appear like, hey, this might be easy. It kind of is, but it kind of isn't, because, well, it looks a lot like Cal 2, doesn't it? I mean, it's just area under a curve, like Cal 2, which in Cal 2, you didn't realize it when we were in Cal 2, but we were actually doing this problem in Cal 2. You didn't realize that the curve that you were dealing with, right? The curve on the ground was just a line segment on the x-axis, and you didn't realize that there was a surface up here, but there was, and you were just dropping a curtain down from that surface down to that line segment. We're doing that, but now you don't have to be on a straight line anymore. Understand? But the setup is kind of the same in terms of, hold on, let me see. Yeah, in terms of this, when you look at the Cal 2 problem, what we did was we took the curve, we did these Riemann sums, right? We did all these rectangles and we added them up, right? We did all this. And we said, hey, if we look at just one of these rectangles, here's one of them. We said the height of this is just the function's value. And then the width of it, we called like dx. And so the area of that would just be the height times the width. And that would be the area of one of them. So if we want the area of the whole thing, we would do an integral that allows you to add them up. And you're just going to add up all those little areas and you go from A to B. Right? That's basically what Cal 2 was about. For us, we want to do the same thing. The difference is that we don't have a straight line segment here anymore. So what happens is on the ground, this is the dx. This is dy. And so we need to actually look at the base of our rectangle as being the hypotenuse of the little triangle on the ground. That's how wide our little slice is. It's not like this one where the base was just dx. Because we're moving along the curve, it's always got to be like the hypotenuse part of this little right triangle on the ground. Y'all see how that's different than what we've done before? Okay. All right, so that's where we're headed. Okay, that's where we're headed. We're not going to actually do this right now. We have 13 minutes, and what I'm going to do is I want to make sure everybody understands parametric equations before we go further. All right, because we need to be able to parametrize different sorts of curves. So I'm going to take a step away from this. You're supposed to cover this in Cal 2, but a lot of times don't really get to it. So parametric equations. Overview here. This is not a full like presentation of this. All right, so the idea behind a parametric equation is this. You have a curve, okay? You have a curve that lives in two-dimensional space where this is X and this is Y. So you've got some curve here. Let's say it starts here and ends here. Okay, so it's like this. We're going from that direction to this, or from that point to this point. A set of parametric equations is some function of t that gives you your x coordinate and some other function of t which gives you your y coordinate. Now we have seen this. It's not like this is completely brand new to us, but I just wanted, there's a few different shapes that I want to make sure we know how to find parametric equations for. So what happens here is like t is a clock running in the background. And then as the clock runs, it starts spitting out x and y coordinates. So it starts spitting out ordered pairs and you move along the curve. So what are some of the common curves that you should know? Common parametric curves.
Like a parabola?
Parabola, okay. Let's start a little simpler. How about a line? Lines. Oops. Lines. Okay, I'm going to do this by doing an example. Let's say that we have the XY plane. And let's say that we have this line right here. And I'm even going to tell you what the equation is. It's x plus 2. That's the equation of the line. How could I draw that with parametric equations? So what would the x function be and what would the y function be? They both have to be functions of t. Anybody know?
would you set y equal to t and then substitute t for y?
Close. Do it the
Or
other way.
the other
Set,
way, yeah.
set x equal to t. So if x is t, then that means that that x right there is going to become t. And then the y would just be that t plus 2. If you graph these parametric equations, you'll draw the same line as this. What if it was this line? What if I told you it was this one? Y equals negative 2x plus 2. Then the parametric would be what?
X equals t,
X is t,
negative 2t plus t.
negative 2t plus 2. Look, this is actually very easy if it's solved for y already. In fact, I can do this even if you give me a parabola. Y equals x squared. Now I realize that this is no longer a line, okay? But if I do y equals x squared and I want to do that, then the parametric for that would be x is t and y is t squared. That'll draw me a parabola. So anytime you have an equation that's solved for y, just replace the x with t, and then the y, just write out the function and just replace the x's with t, and that'll draw it for you. Okay. What about this? Circle, radius 4.
X squared plus y squared equals 2.
Okay, that's the equation of it. Yes, I agree with that. Equals
2 squared.
16, right?
Yeah,
That would be
so-
the equation of this. But if you wanted to draw it with parametric equations, how can we draw circles? We've done something like this.
No, it's cosine x or cosine t and sine t.
Yeah, we did this when we were doing like, well, it was earlier. I remember doing this. We were trying to find the intersection of cylinders, I believe. So if we use here 4 cosine t, 4 sine t, this will draw us circles of radius 4. And we can keep going. I mean, we can keep on, you know, moving through. So let me give you one more. What if I wanted you to give me the parametric equation that would draw this starting here at 0, 1 and ending over here at the point 5, 3. I want you to draw me this line segment. I don't want the whole line. I just want the line segment. From here to here. So I'm going to remind you of this by asking you to remember at the very beginning of class, if we have 2 points, right? We have 2 points, we can always create a direction vector. So if I'm going to rewrite this as a vector function, r of t equals r naught plus tv. Remember that formula from the very beginning of class? Well, r naught here, I'm going to use the 0, 1. And then for v, it's the direction vector, which would be the vector from here to here, which would be the vector 5, 2. And if I put those two together, I'm going to get the vector 5t, 1 plus 2t. So distribute the t and then combine the vectors. And now you can see here that this is my x and this is my y. Right, this is my x component and y component. So those can be my 2 parametric equations. But there's one catch. Because it's a line segment, you have to restrict t between 0 and 1. And you can check it for yourself. If you start at 0, plug in 0 for t, you'll get 0, 1, which starts us here. And if you go all the way to 1 and plug 1 in here, you'll get 5, 3, which ends us right here. And every value of t in between takes us across that line segment. All right. That's it for today. I don't have enough time to really get into anything else. Get going on that mini exam. I know some of you still need a few, so get working on those. Any questions? Okay, we'll come back, what, next week? Is it already Wednesday? Wow. Time is flying. Okay, everyone, have a great day.
All right, thank you.
Yep.
Thank you.
I'll hang out here if
Thank
you
you,
have any
sir.
questions.